Okay, now we're going to study. Here we're going to start with rate reaction kinetics, basically. Now the first thing about reaction kinetics is that we'll just cover the basics first, which is what's rate. Rate is basically described as any change that happens. So it's any change that's happening with respect to time. Yeah, that's what rate is. So how quickly some change happens. Now in a chemical reaction, uh, you can define speed by any change. Every reaction has something changing when it's happening. That change could be anything. It could be any change. It could be a change in mass. It could be change in volume of gas. It could be a change in color. Uh, a change in how quickly something dissolves. If it dissolves very quickly, so that means the reaction is fast. If it's taking a very long time, the reaction is slow. So it could be a pressure change. Reactions happen sometimes. You get pressure changes as well, etc. So it could be any measurable change, as long as that change corresponds to the reaction speed. Okay, so it could be anything. And for example, if I have a reaction, I've got Mg reacting with HCl, and what's going to be produced is that it's going to produce MgCl2, and it will produce H2 gas. Okay, this is a solid. This one is aqueous. This is aqueous as well, and this one is a gas. So, Varda, can you tell me how would you measure the speed of this reaction? What change can you measure with respect to time when this reaction happens?
Is it the amount of hydrogen gas produced, the volume?
Okay, so you can measure the amount of or the volume of H2 gas that's going to get produced. This one. So one change is that you can plot the volume of H2 with respect to time. And normally reactions are faster in the beginning, and then they slowly tend to stop. So at that point, the volume of H2 is going to be that volume of H2 is going to stop changing. Yeah, so the graph is going to be look something like this. So that's one thing. तो इसके अंदर मुझे बताओ कि what exactly is the rate? I mean, what is the thing that you're going to measure? How do you measure the rate of the reaction by looking at this graph?
Would you draw a tangent?
Okay, so the tangent is the rate. Uh, so for example, the tangent at this point is okay, so the gradient is your rate. Or the speed of the reaction. It doesn't really matter whether the gradient is going up or gradient is going down, because there could be changes that are decreasing changes, where points actually decrease as time goes by. Pure change without apart from volume of phase two. What else can you plot?
How fast the magnesium dissolves.
ठीक है. So ठीक है, that's possible. Apart from that, any other thing? Like the mass is going to decrease, right?
Yeah.
ठीक है, so the mass of because the H2 is being released, so the mass of solution what? So the mass of solution would decrease. So if you start off here, the mass of solution is going to decrease very quickly first. Here I says that it's going to stop decreasing. So after a certain point, it's going to stop decreasing with respect to time. And again, the tangent is so the tangent is your rate of reaction. So gradient equals rate. So first point is that it doesn't really matter whether it's a negative tangent or it's a positive tangent. So increasing change, decreasing change is irrelevant. And basically that means that the sign of the gradient or tangent is irrelevant. The value of the tangent is what's important. So that's one thing. And now there's one issue, which is that reactions when they start, they usually slow down. So when for comparison purposes, at what point do you measure or compare the rates? Because it's irrelevant if you compare the rates after like 10 minutes when the reaction stopped, because then there's no point in comparing the rate of the reaction, right? So it's always for comparison purposes, it's always initial rates that are compared. So whenever you're trying to compare, you always compare the initial rate. The initial rate is basically like in the first one. If I draw the initial rate, so you're going to try and draw the tangent right at the beginning. So that kind of gives you your, which is the time is going to be, you're going to try and draw the tangent at time t is equal to 0. ठीक है, ये clear है?
Yeah.
अच्छा, उसके बाद है कि now you've got this thing. So that's one thing. What you can do is when you're trying to measure the rate of reaction, you can plot the entire graph and at regular time intervals. You can measure the change and plot it at regular time intervals. Now, there's another method, which is that you don't have to actually plot the entire, or instead of tracking the change all the time. The second method is, so this one is to avoid the graph. So the other method is, I mean, this one we can call it the graph method of investigating. of investigating rate. Because the second method is, I mean, kind of the same thing, but the second method is, how would you measure rate without graph? So let's say now you don't want to plot a graph. So what you do is that rate is what changed with respect to time, right? Now, one thing that you can do is you can change with respect to time. So, so what you're going to do is you're going to get rid of change. You're going to keep change constant. So that's how we actually measure speed in the real world. Okay? For example, if you've got a 100-meter race, what do? You don't actually measure the change. I mean, if it's a 100-meter sprint for in the Olympics, they only measure time. That's it, and time is inversely proportional to what rate. Okay, they just fix the change. You have a fixed constant change. So keep change constant. You just fix it, and you just figure out who does that quickly. Okay, that's it. So you just measure time. Only time is measured. Is that idea clear?
Yep, it's clear.
So for example, you do overall example. Then for example, what you can do is instead of plotting the volume of H2, what you can do is uh, so find out how much time is needed for let's say 10 cm cube of 10 cm cube of H2 gas to be produced. That's it. तो इसमें ये कि for example you've got experiment number one. In experiment number one, the time that was required was as a labeling has to always done. So experiment number one, experiment number. So in experiment number one, the time required was 155 seconds, let's say. In experiment number two, the time required was like 98 seconds. In experiment number three, the time required was 43 seconds. So which one is the fastest? Which one is the slowest?
The fastest is number 3.
Okay, so basically rate is what it's proportional to 1 over time, right? So it's 1 of 155. This one is 1 over 98. This one is 1 over 43. Okay, so just remember there are two ways of, broadly speaking, there are two ways of investigating rate. This one is the more easier one. That one is kind of the more difficult one, requires a lot more effort. Which one do you think is the better one? Like the one with graph or without graph?
With the graph.
And why is it better?
Is it more accurate?
Yeah, but what's the reason for that? It's just I'll just tell you, like in science, you're always plotting graphs, right? The thing with graphs is that
Yep.
because you've got more data points, so you can sketch graphs. You can remove anomalous values. Maybe if there's a point that's very far away from the graph, you're just going to ignore it. So it's these values, like you're just depending on one data point. That's it. Like experiment number 343 seconds. You can't be really sure that that's 43 seconds. So graphs are always more reliable because you've got lots of data points, and it's a lot easier to actually get rid of anomalous values. Is that point clear?
Yeah.
So that's one thing. अब उस पे आ जाते हैं rate of reaction, like all of the stuff, right? Factors that affect rate of reaction. They're broadly speaking five factors. The rate of reaction is affected by two things. One is that you have these particles, and you have these other particles that go. So it's all up to the collisions of the particles, right? So these particles are colliding with these particles, and they're going to, if they collide with sufficient force, which is the activation energy, that will result in the breaking of old bonds and new bonds are going to be formed, right? So it all depends on the frequency of collisions, and it depends on the effectiveness of the collisions. If the collisions are very energetic, if they have sufficient kinetic energy, then a reaction is more likely to happen. So there are two factors that are involved. So first thing, temperature. Temperature is factor number one. इसका बताओ कि what would temperature do if you increase temperature? What happens? Why does the reaction speed up?
Because the kinetic energy of the particles increases, so there's more frequent collisions occurring.
What about effectiveness of collisions?
Yeah, and there's more successful collisions occurring as well.
So you get more frequent, and you also get more effective or successful, or the proportion of successful collisions increases. Second one, pressure. Why does that?
If if the pressure increases, then the volume decreases, so the particles are closer together, so therefore they collide more often.
So remember this. This only happens in gases. That's it. Pressure will have no effect on solids and liquids, right? So
Yeah.
you have lesser volume. So particles are closer, and what you get is you get more. That's a third one. Concentration, and this is for solutions. This का भी यही होगा कि it's particles are closer together if it's more concentrated, and you only get more frequent collisions. So what does a catalyst do?
Does it lower the activation energy?
So it lowers. So more frequent, what more successful? What happens?
Um, there are more collisions happening because the particles gain more energy.
No, they're not gaining energy. It's just becoming that it's easier for the reaction to happen. So you get more effective collisions.
Okay.
So you get more effective collisions. You get, and the fifth one is surface area. You get so smaller particles have more surface area, and therefore you have more frequent collisions. Okay, so you've got to remember this whether you get more effective collisions. पहले वाले में it's frequent as well as effective, right? Second one, it's just frequent collisions. Again, you've got frequent collisions, effective collisions. And this one is effective collisions. Okay, what is this clear?
Yep, it's clear.
So that's all basics, right? Rate of reaction, right? Now, moving to the rate equation, okay, we have to study rate equation and we have to study the order of reaction. Okay, so we've got to discuss these two things. So now what happens is that if you have a reaction, any reaction, let's say you've got A reacting with B and it's producing C. Okay, so you've got your rate of reaction is dependent on what? Your rate of reaction, and this is specifically for concentration. We're going to come to temperature later on. But first, your rate of reaction is dependent on the concentration of A, and it's also dependent on the concentration of B, right? You've got more concentration of A, the reaction speeds up. You've got more concentration of B, the reaction and the collisions there'll be more collisions, and the reaction would speed up, right? Is that clear that a rate would be dependent on the concentration of A as well as B? Is this clear?
Yep.
Except for one thing, which is that we don't know how it's going to be dependent on it. So there's going to be X and there's going to be power Y. This X and Y is basically your order of reaction. So it's the order of the reactants, which basically it's the exponent or the power of concentration of the reactant. So it could be one, rate could be, I'll talk about the value of X later on, okay? But first thing I'm going to do is, when you're trying to investigate, like how does the rate of reaction depend on the concentration of A and the concentration of B? Remember, if you're trying to investigate two variables, like if I'm trying to investigate how does the rate vary with the concentration of A, like what is the relationship? What I need to do is I need to keep every other variable constant. So if you want to investigate how does rate vary with, like if you change the concentration of A, how would the rate be affected? So one thing that you can do is you can keep B in large excess. If you keep it in large excess, its concentration would in effect become constant. If you have something that's in very large excess, so even if a few particles get used up in the reaction, like if you have like two particles of A and you have got like 10,000 particles of B, then if I mean they're reacting in 1:1, so if one particle of A reacts, its concentration decreases by half. If one particle of B reacts with that one particle of A, then its concentration would barely change, right? Because instead of having 15 particles, you'll now have 14 particles. So it's kind of the same thing. Is that point clear that you can keep one of the reactant concentration constant? Is this clear?
Yep.
Because during the reaction, it will change. So to stop it from changing, you just keep it in large excess. So that in that way, you can basically just consider that as a constant, and you can now sort of investigate like if the reaction goes on, the concentration of A is decreasing. There are two particles, then there's one particle, then there's zero particle, right? B is in excess, so that means it barely changes. So that means the rate is completely dependent on the concentration of A because its concentration is changing, but B remains constant, right? So you can investigate this relationship. Okay, so we want to investigate how does A affect the rate of reaction, right? So the first one is order one. Now, order one means that X has a value of one. That means that rate depends on the concentration of A and the power is one. That means that if you double the concentration of A, the speed of the reaction will double. If you triple the concentration of A, the speed of the reaction will triple. Okay? If you increase the concentration of A 20 times, the rate of the reaction will also increase 20 times. Okay? So this is directly proportional. So this means that it's directly proportional. Uh, double A's concentration, the rate doubles. Is this clear that what does order one mean? Is this clear?
Yeah.
So now, how would the graph of like if I plot A's concentration with respect to time? So if I plot A's concentration with respect to, remember A is your reactant. Now your reactant would usually get used up, right? So as the time proceeds, A is going to get used up. This A over here, it's going to get used up. How do you think would the graph look like?
Would it be like a curve downward?
Outwards, right?
Yeah.
Because A is going to get used up, right? So that's your starting concentration, right? Then it's going to get used up. So where's the half part? Just 1 second. 1, 2, 3, 4. So let's say this is my starting concentration. Now the exact half would be over here. Just 1 second. So then it's 1 second. It's going to be then it's going to be and so on. So anyway, so it's going to be a curve. Okay, that's fine. The A concentration will decrease Anyway, so it's going to be a curve like this. So basically, what will happen is if A concentration decreases, the rate of the reaction decreases. So basically, what is happening here is A concentration decreases. I mean, most reactions they happen this way. Like if you pour Pepsi into a glass, you get a lot of bubbles initially, and then the reaction slowly slows down. You get fewer and fewer bubbles. So yeah, as the concentration of the reactant decreases, rate decreases. And we learned that what is rate? Rate is gradient decreases, the tangent decreases. Everything is slowing down. Okay, so the reaction never seems to end. Like if you pour Pepsi into a glass, initially you get a lot of bubbles, but then you get fewer and fewer bubbles, but it just keeps on going on. It just slows down every time. Okay, so it's like an asymptote. It never actually goes to zero. It just keeps on slowing down. Okay, so is this idea clear? What this graph looks like? Is that clear?
Yeah.
So now, by looking at the graph, there's a concept called the half-life, which is this one that half-life is the time required for the concentration to decrease by half. So then you have the second half-life, which is second half-life is the time required for the concentration to decrease by another half. Then you have the third half-life, which is the time required for the concentration to decrease by half once more. Okay? So you would notice a pattern, which is that the half-life is constant. This is your first half-life. This is your second half-life. This is your third half-life, right? And you can just keep on extrapolating this equal banality. So my fourth half-life, that's exactly the same. So every time it's a constant half-life. For what? For a first order reaction. So what you can simply do is you can just plot a graph and see how the concentration of the reactant and the speed of the reaction, or how does the concentration of the reactant vary with respect to time. So you can just figure out or plot a graph of that, and the shape of the graph or the measure of the half-life would actually tell you whether it's order one or not. Is that clear?
Yeah.
So similarly, there's order zero as well. So the same relationship would have a zero order relationship as well. A zero order relationship means that what does it mean? It means that the rate of the reaction is dependent on the concentration of A, but the power is zero. What kind of relationship is this? What does that mean basically? Like if I change the concentration of A, what is going to happen to the rate of the reaction?
Um.
If something has a power of zero, it's
Isn't it just one?
always one, right? So that means no matter what the concentration of A is, the rate of the reaction will remain unaffected. So if A concentration changes, absolutely nothing happens to rate. You always get one, right?
Yep.
So absolutely nothing happens to the rate of the reaction, and now the graph for this one would look like this. That Now, in this case, there are very few reactions that are actually zero order reactions. Normally, what happens is that whenever you change concentration, the rate of the reaction gets affected. But sometimes it doesn't get affected. There are reactions which are zero order reactions. We're going to discuss them later on. That the speed remains completely unaffected. So their graph has a constant tangent. It doesn't slow down. It just keeps on going. As the concentration keeps on decreasing, the speed of the reaction just you've got a constant speed. So that means you get a constant gradient, which is basically your rate. Is that clear?
Yep.
And similarly, the last one that's order two. So we're going to do the graph for order two. So maybe the concentration, the rate of the reaction is dependent on the concentration of A, but the power is 2. इसका क्या मतलब? If I change the concentration of A, what will happen to the rate? Like if I double the concentration of A, what will happen to the rate?
Would it also be doubled?
But it's squared, right? So that means it's going to be quadrupled. Like if I double करता हूँ, if I put 2A over here, it's going to become squared. So it's going to become 4 times, right? Is that clear?
Oh, okay. Yeah.
So this one means that it's actually too dependent on the concentration of it. I mean, the first one was directly proportional. If you double this, you double this. Now it's you double this, you quadruple this, right? So it's if you decrease the concentration by half, this will slow down by a much bigger extent. So this means that if you double A's concentration, it quadruples. So vice versa, if you triple A concentration, the rate becomes 9 times. If you halve the concentration of A, it becomes 1/4. Is that clear? Or
Yep.
इसका बस जल्दी से ना we'll do the graph what would the graph look like? So if I plot A's concentration with respect to, so now the only difference is, let me just count them. This is 4. I think it's starting concentration. Okay, the only difference is, and it's going to slow down if A decreases by like initially the reaction is like very fast. Okay, so it took 3 seconds for the concentration of A to decrease by half. Next time, now the reaction would slow down too much, right? But अगर उसकी concentration half होती है, the rate becomes 1/4. So it's going to take double the time now. So now it's going to take twice the time for the concentration to decrease by half again. इसके बाद it's going to take 3, 3, 3, 3. So it's going to take double the time for the concentration to decrease by half again. Okay, and so on. Okay, so it just slows down too much. उसके बाद क्या होगा? It's कितने दिन पहले 3. अब काफी ज्यादा होगा 3, 3, 3, 3. यहाँ पे जाके आ रहा है. So basically, reaction is सबसे लास्ट है कि तो ठीक है. अच्छा, basically what's happening is that the half life is doubling. The reaction is just slowing down too much. जैसे जैसे it's getting used up, it just keeps on slowing down. So this is T half life, the first one. This is the second time it decreases by half. Third time, fourth time. So each half life is double the previous half life. Okay, Varda, is this clear?
Yes, clear.
बस ये तीन चीजें ठीक है. Firstly, you've got orders. Rate depends on concentration of A. That's directly proportional. No matter you do anything to A, the rate increases by a proportional amount. A concentration is zero order. That means you do anything to A, nothing happens to rate. Okay, the graph is going to look like this. This is A concentration order 2. You double this, the rate will quadruple. You make it 1/4, the rate will become 1/8. So there's going to be a much bigger effect on the rate of the reaction. So in that case, the half life doubles. ठीक है, तो बस यहाँ पे छोड़ देते हैं. Let's continue tomorrow. ठीक है.
Okay.
Okay, take care.
Okay, thank you.